Hello everyone, welcome to CSE Core Concepts. In the series of data structures, precisely we are talking about nonlinear data structure graphs. In my last video, I have discussed about an important algorithm, Kruskal's algorithm, in order to find out the cost of a minimum cost of a spanning tree. Now in this video, I am going to discuss about the Prim's algorithm. Similar to that, we are going to find out the cost of a minimum spanning tree, but in some other way. As I spoke about Kruskal's algorithm, Prim's algorithm is also a greedy algorithm. That is, it will try to find out the local best options in local best values in a hope that it will find a global best solution. Now in this approach, we are going to start with a single node and we are going to explore all the adjacent nodes of that node and connecting edges at every step. That is, if a node has been added, and even if it does not qualify as a minimum cost, but it will be carried forward to the next step. And we are going to find out only those edges we are going to select which satisfy the condition of minimum weights and no cycles. If a edge has a weight minimum, less weight, but it forms a cycle, then it won't be considered. So consider this graph. It is an undirected graph and weighted. The weights represent the cost of reaching from one node to another node, and there are 9 nodes. We start with the start node, let's say 0, and we have to find out the minimum spanning tree here, fulfilling the condition that no cycles should be formed and the cost should be minimum as possible. So let us start with the 0th node. Now we have to first figure out who are the adjacent nodes of 0th node. 0th node adjacent are 1 and 7. So what are the weights on them? From 0 to 1 the weight is 4, and from 0 to 7 the weight is 8. So we have to select the minimum among these two. So 4 is the minimum among these two. So we will select the 0 to 1 edge. So you can see my edges connecting to the MST are 0 to 1 and 0 to 7. So minimum weight among 4 and 8 is 4. So I am going to include vertex 1 in MST. What is MST? The minimum spanning tree which I am going to create. Initially there is no tree, there is only one node, that is the 0th node. So gradually as the nodes get selected, I am going to go on adding it to the minimum spanning tree. So in the first iteration I am going to add node 1 having weight 4. Now in the second iteration I am going to find out the adjacent edge nodes of node 1. So who are the adjacent edges of node 1? That is 7 and 2. So for 7 and 2, what are the weights? 8 and 11. So of course I am going to include 7 and 2 to find out, but I am not going to reject the earlier one, that is 0 to 7. See, in the previous step we had two edges, 0 to 1 and 0 to 7. So we selected 0 to 1, fine, because it was having a minimum weight. But we are not going to discard 0 to 7 as of now. We are going to carry it forward to the next step because it may fulfill the minimum weight criteria in some of the iteration. So in the next iteration we have three values to be compared, that is 0 to 7, which has come from the earlier iteration. For this node 1, the two adjacent edges are 1 to 2 and 1 to 7. What are the weights associated with them? They are 8, 8 and 11. The minimum is 8, which is being shared among two vertices, that is 0 to 7 and 1 to 2. Now in such case you can select either one of them, that's perfectly okay. So we are selecting the 7th vertex. You may have included 1 to 2 also, not a problem. So we are selecting from 0 to 7 having weight 8. Now in the next step I am going to figure out the adjacent neighbors of node 7. Who are my neighbors of node 7? Let's go back and find out. 8, 6, 0 and 1. 7 has 4 neighbors, 8, 6, 0 and 1. Now 0 and 1 are already been used. So I am going to talk about 6 and 8 only. So let's go and find out. I am not going to go back. So 1 to 2, 1 to 7, they have been coming from the earlier iterations, And for this node 7, current node 7, we have two adjacent which we are going to consider, that is 7 to 6 and 7 to 8. We are not going to consider 7 to 0, or because 0 to 7 was there, right? So we are not going to consider it. We have already used that one. Okay. So minimum weight among 8, 11, 1 and 7 is 1, which is of vertex 6. So I am going to include vertex 6 in my MST. Let's see how does it look. Yeah, it looks like this. Now the next node which we are going to consider is 6th node, and for this 6th node we are going to find out its neighbors. So who are the neighbors of 6? They are 6 neighbors are 7, 8 and 5. But we won't go to 7 because it has already been used. Okay, so we are going to consider only 8 and 5, right? So from the previous iteration, the vertex have to be considered, whichever were there, excluding the one which got selected. Apart from that, we are going to add 6 to 5 and 6 to 8. So among all of them, 2 is minimum. So we are going to include 2 is for whom? 6 to 5. So we are going to include vertex 5 in our MST. So it looks something like this. Okay. Now in the next iteration I am going to figure out who are the neighbors of 5. So the neighbors of 5 are what? 6, 2, 3 and 4. Now 5 to 6 I am not going to use because obviously that has already been traversed. So I am going to include 2, 3 and 4, right? And also the previous ones, right? So 1 to 2, 1 to 7, 7 to 8, 6 to 8, 5 to 2, 5 to 3 and 5 to 4. Up to 6 to 8 it was from the previous iteration, and this iteration includes 5 2, 5 3 and 5 4. So the adjacent, the weights, associated weights have been written, and 2 is the minimum among them, which is for the edge 5 to 2. So obviously I am going to select the vertex 2 in this case. So it looks like this. Now the next step what I am going to do is that I am going to find out the neighbors of 2. So let's go back and find out the neighbors of 2. Neighbors of 2 are 2 to 1, 2 to 8, 2 to 3, 2 to 5. Now if you realize here 2 to 1, if I am selecting this and it may qualify, then what will happen? See, what will happen here if I am using 2 to 1 and suppose it gets qualified, then what will happen? It will form a cycle. So I cannot select that edge which can form a possible cycle. So I will eliminate this 2 to 1, I will not consider, but I will consider its others neighbors like 2 to 8, 2 to 5 and 2 to 3. And then I will select the minimum among them, right? So I am not selecting 2 to 1 because it will form a cycle. Other than that, I am selecting 2 to 3, 2 to 5 and 2 to 8, and the other one, the minimum is 2, which is used by the edge, which is the weight of the edge 2 to 8. Okay, so I am going to include 8 in my list C. Understood? Now I am going to find out the neighbors of 8. So what are the neighbors of 8? 8's neighbors are 2. I will not use that because already there is that edge has been included. 7, 8 to 7, okay, I may not. Let's see why not. 8 to 6. Now if you realize, if I am using, in this case, if I am using 8 to 7, let's say 8 to 7, will it not form a cycle? 8, 7, 6, 5, 2 and 8. That will form a cycle. 8, 7, 6, 5, 2 and 8 will form a cycle. In case I am using the edge 8 to 6, 8 to 6 will again form a cycle among 8, 6, 5 and 2. Okay, so I am not going to include these neighbors. So which neighbors are remaining? Let's see. I cannot use 8 to 7. I cannot use 8 to 6. That's fine. I cannot use 8 to 2. Right. So what will I do over here? So the next one which I am going to do is that, see, I will 1 to 2 and 2 to 8 will be, 8 has been already selected. So now I will have to, cannot include 8 to 6 at it will form a cycle. So obviously we are going by 1 to 7, 7, 5, 3, whatever is there among us. We are going to select the minimum among them, that is 7. It is being shared by two edges 8 to 7 and 8 and 2 to 3, right? Now since 7 and 8, okay, 8 to 7 you cannot have because they are already included. So what we will do here is that we are going to use 2 to 3. That is why we are retaining the earlier vertices values also. Understood? See, in this case what happened? 8, if the neighbors of 8 are 6, 7. But 6 and 7 both I cannot include because 8 to 7, 7 has already been included. I cannot, it will form a cycle. 6 I cannot. Okay, so I have to select from the remaining ones. So from the remaining ones, 2 to 3 qualifies because it has the minimum value. So it will become 2 to 3. Understood? So you do not have to always go by that vertex where you stopped. Last time we stopped at 8, and generally what we have been doing is that from 8 you have to select its neighbors and you have to find out. But here in this situation what is happening? From 8, anyone if you connect, it is forming a cycle. I cannot do that. So I have to select among the others, right? So we are going to select between them, and if the value is 3. And finally only the vertex 4 remains to be included, and the minimum weight from 4, because 4 has only that neighbor which is remaining. Okay, 3 has only that neighbor which was remaining. Let's go. 3 has neighbor 5 which has already been included. 3 has neighbor 2 which has already been included. So only 4 is remaining. So obviously even if it is not a minimum value, okay, but we can always use that. Minimum value from 3 is 7 to 2, but we cannot take it because it will form a cycle. So we have to select only 4, okay, even though the weight is more. Understood? So this is how we are going to connect to the minimum spanning tree. So if I want to calculate the cost, we are going to add up all the weights. Okay, so if the minimum spanning tree something looks like this, right? So what are the weights? 4 plus 8 plus 1 plus 2 plus 2 plus 4 plus 7 plus 9. The value comes out to be 37. Okay, I hope you understood. Please try to do it on, solve it on your own following my video. Then only it will be more clear to you. Just make sure that no cycles should be formed, okay, and the minimum cost has to be taken. But sometimes, as in our case, what happened, that 3 to 4, okay, it was not the minimum value, but I could not opt for any other node because of the other restrictions. So in that case we had to go for other option. And another thing what we faced here is that about node 8. Node 8, whatever neighbors it were having, all were forming a cycle. So I could not use it. So that is why here it is important to retain the earlier edges and include them also for finding out the minimum value. Thank you for now. In my next video, I am going to discuss about a algorithm to find out the shortest distance, that is the Dijkstra's algorithm. Thank you.